A third example that we can go through is carbon dioxide, CO2. Again, let's go back to the steps. First step is we must determine how many valence electrons we have available to us. So we've referred to the periodic table for this. And we find the elements, and then we look at their group number. So again, carbon's in group 14, carbon brings in 4. My oxygen shows up in group 16, it brings in 6. I have 2 total oxygens in this compound, plus my 4 gives me a total of 16 electrons to work with, or in other words, $16 to build my structure. In this situation, we have carbon and oxygen. We can look at a number of things here. We can look at lower electronegativity, carbon. The one that likes to form the most bonds, carbon. We can look at the ratio. So 1 carbon every 2 oxygen or lower oxygens. The lower number of the ratio goes central. So all 3 examples work here. So we're going to put carbon central, and we're going to attach the oxygens on either side of the carbon by single bonds. So again, keep your budget. You just spent $4. So now you have $12 remaining. In order to accomplish our goal, to make sure everything has a full octet, once again we do an electron check. We realize that once again these oxygens have single bonds. So that both the oxygens on the outside are acting as if they have 2 electrons. They both want 6 more. The carbon in the center has a single bond on either side. It acts as if it has 4, so it wants 4 more. In this scenario, we then realized as we did our count that we actually need 16 and we only have 12. So now we have a deficit of 4. With a deficit of 4, you have 2 options. You can make 1 single bond into a triple bond, or you can make 2 single bonds into double bonds. Carbon dioxide, in figuring out which one you're going to use, one of the techniques to determine it is to consider the formal charges. And we'll talk about an example of that later on. Another way, and a quick check, is that I gave you a chart, and we realize with the chart, as we figure out how many bonds each group prefers and how many lone pairs, we realize that oxygen in group 16 loves to form 2 bonds and have 2 lone pairs. So we're going to start out and do this structure, changing 2 single bonds into 2 double bonds. We will come back and take a look at, I'll show you the triple bond, changing 1 single bond to triple bond at the very end. And it actually does work out, but this in all realities we'll figure out as you continue on and take a look at formal charges later. We'll realize that this is the correct structure for carbon dioxide. So again, we just bought 2 more bonds, so we have to keep our budget. So we just spent an additional $4. So we spent now $8 total. Now we have $8 remaining in our budget in order to accomplish our goal. Once again, that everything has a full octet. So in this situation, now both the oxygens on the outside have double bonds. And so both of them have 4, and they want 4 more. So that gives us our total of 8. Your central element, your carbon, has a double bond on both sides, adding up to a total of 8. The carbon in the central atom is happy. So we realize we need 8. We have $8. So the last step is buy them their electrons. So we buy the 4 electrons for the oxygen on the left, 4 electrons for the oxygen on the right. Remember, we buy them in pairs. Do a final check. 2 last things, final check. First of all, we check to make sure all of the atoms in the compound have their full octet, and then we do a double check of the total count at the very end. And so first of all, we see that again this oxygen on the right has again total of 8. Remember, the bonds both account for 2, and then the 4 dots. Both the oxygens have 8, and the carbon in the central has 4 single bonds around it, therefore or 2 double bonds, so it has a total of 8 as well. So everyone's happy in this situation. And then if you do a final count, you will realize that the final count does add up to 16 electrons, so you did spend your budget. And everyone has a full octet, you're happy, you're done. Now remember, I told you, we had a deficit of 4, we had a choice, 2 single bonds into 2 double bonds, or a single bond into a triple bond. In this situation, we see the triple bond and how it unfolds and how the structure will look. The reality behind this is that the structure would actually work out this way. But we'll find out more with formal charge that because of formal charge, we'll realize the one on the left is actually the correct format for carbon dioxide.